This is AP Calculus BC, lesson 4-9. This is Euler's method. Today's date is Monday, April 27th, 2020. So our objective today is to use Euler's method to approximate y values using various step sizes of x. Okay, so there's a bunch of y's here. So why do we need this? Why are we learning this math? So sometimes differential equations can't be solved analytically. Kind of squeeze that in there. And that means doing the separate, integrate, isolate, evaluate. I think those steps are from normal AB calculus, so I'm kind of speaking gibberish to most of you. But sometimes you just can't solve it using the mathematical methods that we've talked about in AB calculus. So we have to have a different way of doing it, and this is the only way that we really have of solving it, is using some sort of numerical method. So I'm going to write this off to the side. This is a numerical method. This is one of the first and easiest types of numerical methods, and you need to have a computer in order to use it. Otherwise, just doing it by hand will take forever. So how does this work? The general idea is, if you know what the derivative of everything is, and again, it's impossible to solve. Obviously, this one is super easy, and you could solve it analytically. But let's pretend that this was hard and we couldn't solve it analytically. How would we solve it? So we have some information that we start with. It says, hey, here's your starting point, and here's the derivative. Go ahead and see what this derivative looks like. Can we graph this thing just having a tiny little bit of information? So let's go through this. Let's go through the procedure of Euler's method. So what information is given to us? We know that the x value is 0 and the y value is 1 for our initial point. So I can say my x value is 0, my y value is 1. And I can graph that point too. I want to be able to connect what we're doing here to the graph to visualize this. So I start with this point. Okay, I also know what the derivative here, this dy dx, you can maybe sometimes call this y prime. This derivative, this y prime right here, I don't have to cross it off, but that's the same thing as y prime, is just y. And most of the times it's written in terms of y and x. You can see in future examples I'll be given like 3x minus 2y. I gave you the most basic one that I can think of, just equal to y. So what is y? Well, the y coordinate back here was 1, so y prime therefore is also 1. And these two columns here will always match, just for this easy example, which means that for however big my step size is, the slope is 1. I don't know how big of a step size to do. If you want to be really, really accurate, you want a really small step size. But I know that if I have some sort of line now, from this point, it has a slope of 1. So right one, up one, right one, up one, however long I want to go. I get to choose my step size. And what do I mean by step size? What I mean by that is, how much do I want to increase x here? And you get to choose. Well, oftentimes in Khan Academy, they choose for you. Like this one says a step size of 1. But in the real world, you get to choose whatever step size you want. So for our simple math, I just want to do 1. So let's go ahead and say that our delta x, our step size, is just 1, which means I'm going to add 1 in this step here. So 0 plus 1 is 1. I could have chosen any number. Okay, so if I step up by x is 1, what's happening with y? Well, y had a slope of 1, so again, if you thought about that line, I'm now cutting it off right here. I'm saying, hey, my y coordinate is 2. Well, how do you get that? Just from the table, because again, you're going to be doing this purely from a table for the homework. You're not going to have a graph. How do I get that just from the table? Well, I take my old y coordinate and I say, I'm going to add these two things multiplied together. I'm saying the slope times the, well, I guess it's not really the x coordinate. You're really multiplying this step size by the derivative, by your y prime, and 1 times 1 is just 1. So I'm going to add my starting point. This was, oh, I wrote that so crooked. Your starting y coordinate, and then I'm going to plus our 1 times 1. 1 times 1, and there's lots of ones here, and I realize that's confusing, but those ones came from our slope and our change in x, our step size. Okay, and then that's obviously equal to 2. So the y coordinate is 2. I can graph these points 1, 2. So 1, 2 is right there. And let me go ahead and erase all these extra lines that are happening here. I now have a line that goes between 0, 1 and 1, 2. So what I need to find the new y prime, because that's how I'm going to find my next y coordinate. I mean, I can find my x values. You have to have a constant step size, by the way. So if I chose 1, it has to be 1, then 1, then 1. So I can fill this out to infinity. It's really easy. But these two columns are the difficult ones. So in order to find this value, I have to find this y prime first. So again, this is just using the formula. Y prime is just the y coordinate, as I said before. So this is just 2. Okay, so that means that this point right here has a slope of 2, and it goes right 1, up 1, and you can see from the graph already, we know what the y coordinate is going to be. It's going to go up this direction. It's going to have the coordinate 2, 4. So the answer is 4. But how do you get that just from the table? Again, you take your old y coordinate 2, and then I add this derivative, or the slope, times your change in x. So 2 times 1. 2 times 1. And that is 4. Okay, the math checks out. And then you find your y prime again, then you do it over and over again, and then you would eventually find this out to infinity if you want, but it gets less and less accurate. Let's just try one more to make sure you guys got it. So again, I'm doing a step size of 1, so plus 1. And what is my new y prime? So I'm plugging in, it's just the y, right? So this 4 is copied over here. So my new slope is 4. So on my graph, I can even check what this is going to be. It's going to be right 1, up 4, 1, 2, 3, 4. So I know my y coordinate is going to be 8. Let's check that we can get that analytically without just graphing it. So I take my old y coordinate 4, and then I'm going to add my slope times my my step size. So it's going to be 4 times 1, and that is indeed equal to 8. And then I do it again and again and again. You guys get the idea. Now the question is this accurate? And the answer to this question is no, because our step size is so gigantic. Like 1 is pretty big. In fact, let me pull up what we just did here in GeoGebra. So we have this equation. If you actually do the separate, integrate, isolate, evaluate using that analytic method, you actually get the equation e to the power of x. So what does that look like? That's what it looked like. So obviously we had the initial point correct because that was a starting information, but the farther and farther we go from that initial point in terms of x, we get more and more error. Like look at the distance between our c value and or like the C point, it has a height of 4 when it should have had a height above 7. It's off by a factor of 2 already, and it gets worse and worse and worse. But obviously if I choose smaller step sizes, it gets better and better. What if instead of choosing plus 1, I chose 0.5 or 0.01 or 0.00001, and I just had the computer do this? It gets really, really accurate. So you might kind of notice that I'm a little bit more passionate, maybe not, but this is me. Like when I went to college, I studied applied math, and this is applied math. Why? I can apply numerical methods to almost everything in nature. Specifically, I'm thinking of the Tacoma Narrows Bridge, which I'll talk about in a second. But you can do this for anything that you want to really model in the real world that sounds difficult. Like if you want to find like what the critical load is for buckling a column, like what is the statistical analysis of scaffolding, what is the natural frequency of a vibrating bar. A ton of like these really hard questions can be answered all with this numerical method. Obviously not this one because it's not that efficient. You could maybe use Newton's method or the bisection method or Jacobi method or Jacobi integration. There are a ton of these, and you can calculate things like this. So let's pull up the Tacoma Narrows Bridge. So before I play this video, a little bit of background. So the Tacoma Narrows Bridge is in Washington, and in 1940 the wind was blowing at the right speed that made it vibrate more and more and more, and it eventually collapsed. And if people were applying the correct numerical methods to the construction of that bridge, it wouldn't happen. And bridges today use numerical methods so that it doesn't happen. In fact, one of my final projects for my 4th year of studying math at UC Davis was to recreate the Tacoma Narrows Bridge using math to show why it happened and what should have happened differently in its construction. And it was a super fun project. So that's what the Narrows Bridge looked like, the Tacoma Narrows Bridge. Well, let's watch the video of it getting destroyed because that's kind of fun. I skipped over the video. Where is it? There it is. Disaster. Oh man, what a great video. If I full screen this, it's super pixelated, but there it is. So the wind is going, I don't remember which direction, but obviously it's going from left to right in terms of our perspective, and it's vibrating this bridge more and more and more. And I should point out, these are steel cables. This is concrete. This is a heavy, heavy bridge. By the way, the owner of that car got like refunded for the car, and I think there's like an animal inside of it. I don't know exactly what happened, but it's crazy. This bridge eventually does collapse just because wind was vibrating the bridge. Yeah, I'm saying multiple words at the same time. Let's skip ahead to where it starts collapsing. So it vibrates so much that it just, yeah. I can model this. You can model this if you want to study math at a higher level. You can model really hard things like this using numerical methods. All right, so that's my little bit of trivia about today's lesson, which makes me really excited to teach it because it's bringing back all these good memories from college. Well, also the bad memories too. This was probably the hardest, or maybe the third hardest class I ever took, and definitely the second most fun class I ever took. The first being linear algebra. If you ever want to do that, it's like a closed system, which is super cool. Anyway, okay, so let's get back to how do we do this on Khan Academy. So let me give you the general procedure. So you always want to make a table of x and y values and also your y prime or your dy dx values. You always want these three columns. Sometimes Khan Academy has like an n value because your x values are a little bit weird, but these are the three columns that you'll use. So let's say that the problem gave us some starting information. I'm just going to say x naught, that's our starting x. It might be 2, 1, it's just some number, and it also gives us a starting y. Sometimes that y value will be a variable, like in example 2, but they'll give you some sort of y coordinate. So the first step that you're going to do, maybe I can do little numbers for steps. The first step that you're going to do is just plug in. You're going to plug in both your x and your y, like you have it in here, to figure out what the derivative is. Okay, well then I guess step 2 is to figure out what your new x coordinate is. So again, you're going to have some sort of step size. I don't know what that is. I'm going to call it delta x. How much are you changing in x? Sometimes they tell you in the problem, use a step size of 1. That means delta x is plus 1, but generally speaking, you have that original x, and then you're going to add some sort of step size, and then you're going to, let's say that that's x1 now, then you're going to do that old x1, and again, add on your step size. Step number 3 now is, this is probably the most tricky part of Euler's method. You have to use the number that you got from your derivative, your slope, and you have to add that with the old y coordinate, but accounting for the size that your step size. And that is easy whenever your step size is 1, but in example number 3, I specifically make a step size with a decimal, and I know it's hard, but Khan Academy does a ton of those, and they're kind of annoying, and you should be able to know how to do them. So what do you do for step 3? Well, you take your old initial y coordinate, so your y is 0, and then you add your delta x, your step size, times, I guess we did it in the other order, I'll follow the order that we did above. We plugged in our, well, plug in to get your y prime naught, I guess, and then we're taking that y prime naught that you found in this step up here, and then you're going to multiply that by whatever your step size is. And again, I always forget that sometimes the step size is not 1, so just make sure that you're remembering multiply by step size, and then again, you're just going to, step 4, you're going to plug in again. Plug in to get your next derivative, so we'll call that y1, and then you do the same thing again. So I guess this is step number 5, and then step number 6, you're going to do, let's call this whole thing a y1. So you're going to take this value right here that we're calling y1, so you'll take that y coordinate, and then you're going to add on this times your step size. So your y prime 1 times your step size. And then usually you don't have to do that final last box because it's pointless. Like, you found your answer, it was that one. Okay, that's a very general way of doing it, but I always think about it in terms of a graph. It makes a lot more sense to me. Hopefully you do too. You try using a graph, that is. Okay, so this is like a Khan Academy type of problem. So we have our derivative, we have our initial value, which is a variable, and it's saying, okay, let's do Euler's method. They're going to start x is equal to 0. So let's go ahead and set up our table. So we have an x, we have a y, and we have, I'm just going to call it y prime because I'm lazy, I don't want to write dy dx. We know that our x coordinate starts at 0. It tells us that right here. When I plug in 0 into my function, I get out a y value of k. So my initial y value, I can come down here and say my initial y value is k. That's it. That's all it's given us, aside from the fact that we know the derivative. The derivative is 3x minus 2y. So I'm plugging that in. Maybe I should write that up here. We're doing 3x minus 2y to get this value. That's what we're plugging into. So what's 3 times 0? So this is 3 times 0 minus 2 times k. And let's simplify that a little bit. That's just negative 2k, because 3 times 0 is 0, etc. So next, we need to figure out what a step size is. So it says the step size is 1. So that means from this 0, I'm going to add 1, the step size. And maybe I should make a note that my step size here is 1, which means it's nice and easy. So x value is 1, then I'll get to 2 eventually, and that's what we're trying to find, right? G of 2, we know the answer is 4.5, so I can even come down here and say the answer here is 4.5. Oh, that's not where I want to write it, because that's y prime. We know that the answer right here is 4.5, but I want to get it in terms of a variable, and then we'll solve. I'll make a note to myself that this answer is 4.5 right there. Okay, so the hard part now. I'm going to take that old k, and let me write this a little neater. That old value of the y coordinate, and then I'm going to add this multiplied by 1, which is just adding negative 2k, or just adding negative 2k, and our final answer for our new y coordinate is negative k. Okay, so again, you're plugging in to this derivative, which came from up here, that derivative to get this spot right here. So what is the x? The x coordinate is 1 now, so it's going to be 3 times 1 minus 2 times the y coordinate was negative k. Simplifying, this is going to be 3 plus 2k. Okay, again, the step size is 1, so plus 1, and this is going to be 2 now for x coordinate, and we're done. We don't have to go any further because the 2 is the final x coordinate. And how am I going to do this? I'm going to take my old value of y. My old value of y was negative k, and I'm going to add on this times the step size, which again is just 1. So I'm going to really add on 3 plus 2k. So plus 3 plus 2k. And if I simplify that, let me simplify it, and I'll use a different color here. If I simplify that, I get 3 plus k. 3 plus k. And I know that 3 plus k needed to be equal to, this 3 plus k needed to be equal to 4.5. So subtract 3 from both sides, and this implies, I'll do this in red, our final, what just happened? This implies that k is equal to 1.5, which makes this equation true. 3 plus k is equal to 4.5. All right, so that's a very typical problem that you'll see on Khan Academy. Let's try another one that's slightly different, slightly harder. Okay, so this one, it gives us initial values that are pretty straightforward. So we'll say I have an x, I have a y, and I have a y prime. So let's make our table. I don't know how big to make this thing. We'll go about that big. So my x coordinate starts at 0. So can I do Command Shift Z? Nope. Okay. Reach about the line. My x coordinate starts at 0. My y coordinate starts at 1. That's just from this information right here. Let's plug those into 2x minus y to get our y prime. So 2 times 0. So 2 times 0 minus that 1 that I'm plugging in. That's equal to just negative 1. Okay. Now this is the tricky bit. Our change in x, our step size, is not 1. Because it says, okay, we need to find h of 3 with 2 steps. So here's the first step, here's the second step, and we need to end at 3. Well, what should I add each time in order to get to 3? Well, 1.5. 1.5. And they'll never make the math to get here that hard. But my step size is hard now. I'm going to be multiplying by a number other than 1, which makes this a little bit weird. So this is, my new x value is going to be 1.5. So how do I find this y coordinate here? Well, I'm going to take my my original y coordinate 1. So let's write down 1, and then I'm going to add on this times my step size, my slope times my step size. So plus negative 1 times 1.5. Okay, and negative 1 times 1.5 is just negative 1.5, so the answer here is negative 0.5. Okay, so we have our x and our y. Let's plug it back into our derivative to figure out what our new y prime is. So 2 times our x coordinate, which is 1.5, minus our y-coordinate, which is negative 0.5. And what is that going to be? So this is going to be 3 plus 0.5, which is just 3.5. Okay, so next step, we need to figure out what our new y-coordinate is, and that will be the answer, right? So I take my old y-coordinate, which was negative 0.5, and I'm going to add on this slope times the step size. So plus the slope 3.5 times the step size of 1.5. And that'll be my answer. Okay, so let's do this off to the side. Wait, 3.5 times 1.5, that's 5.25. So this is going to be negative 0.5 plus 5.25, and that is just 4.75. That's the answer we're looking for. So I can approximate h of 3, 4.75. Whew, okay, so that was a lot of math, and I know that Euler's method is difficult. It's our first dip in the pool for numerical analysis. Good luck, and I'll see you guys tomorrow.